Hey guys, what's up? My name's Dustin Watts, and I'm going to be talking to you today about springs, more specifically slinkies, and how they behave when they fall. Because as you'll see here in a minute, slinkies fall with a very peculiar behavior, something that physicists have been fascinated with for a long time, and that they have explained actually quite well. So, what does happen when a slinky falls? Well, let's watch this little short clip and find out. So as you can see in this video, the slinky falls very weirdly, in my opinion. The top of it comes down, but the bottom of it stays perfectly still. So that, like, as the top is falling, the bottom of it's just staying still until the top of the slinky hits the bottom of itself. Now that's very cool in my opinion, and it must be in other people's opinions as well because they've went ahead and explained it using mathematics, which is what I'm going to try to convey to you guys, and hopefully you can understand it near the end of this video. Now you can picture a slinky like this. It's like four masses connected with springs, or however many masses you want. Doesn't really matter. But each mass has a spring, and so they're attached to each other. And what this means is that each experiences two different forces, a tension and a force of gravity. But sometimes the tension and the force of gravity aren't equal, and that's, force equals ma. That's when it starts to accelerate. And so when you let go of the slinky at the top, it starts to accelerate downwards. But as you can see, not all of the slinky starts to fall at once. And now you might wonder why that is. Well, first off, one of the first easiest physical explanations for this motion of the falling slinky is to say that a wave is propagating down the slinky. What I mean by that is when the slinky experiences the force of gravity, it starts falling at the top, but that information takes time to reach the other pieces. So the other pieces, like I showed before, the other masses that are still experiencing the tension because they haven't known that the block above them has started falling yet, so they're still experiencing that tension. So it takes time for the wave to propagate and for the other blocks to realize, oh, the block above me has just started falling, so I should start falling. Until that wave reaches them, they're still just sitting there with their forces balanced, floating in space. Now, of course, that doesn't really explain the motion that well. I mean, of course, the wave propagates, but what kind of wave are we talking about? Well, I mean, we see here there's been plenty of papers on this, and this is just one of the most interesting ones I found because it mathematically talks about a mass element right here, m delta, some strange symbol I don't really know, and it describes here the equation of motion for a mass element at a location described by that Greek symbol. So what this is telling us is that there is an equation of motion for a mass element at a certain location on the slinky. So like I showed before, the four blocks actually, is it's a really good approximation of what's actually happening because all of those mass elements have a certain equation of motion, and that motion is the wave that's propagating, the wave of the motion of the blocks falling. So you see here is another picture of a man dropping a slinky, and they talk about the tension that there needs to be to hold the spring up, the minimum tension that is achieved, and it talks about non-Hooke's law behavior because, of course, this is a slinky and it's not going to behave like we always want it to in the theory of physics, I should say. Now, going along with what I just said, as you can see here in this little short clip, we can see the center of mass represented by a red dot. And what happens is when the slinky starts to fall down, the center of mass moves down with it. And what that's saying is the center of mass of all of these different blocks that I showed earlier, they represent different masses. And so as those masses start falling, the center of mass itself of the whole spring starts changing position. And this also describes the motion of the slinky and the wave that's propagating, the mass wave that's kind of propagating through the slinky. So if we split the center of mass up into three parts, we get a center of mass for the top of the slinky, a center of mass for the center of the slinky, and a center of mass for the bottom of the slinky. In this case, the slinky is just hanging there oscillating, which is why you see the top of the slinky center of mass not moving because we're holding it there. And the middle is, of course, oscillating, so is the bottom center of mass. Now, this was not done by me, of course. It was done by someone else on, this is from Wired.com. And what he does is he also plots it when the slinky is falling, which is really what we're interested in. So if you look here at the center of mass, the top of the center of mass represented with blue, the middle center of mass represented in green, and the bottom center of mass represented in red. What we see here is linear for the top center of mass. It's really straight for the bottom center of mass until it reaches about 0.1 seconds. And then after that, we have a parabola, just like the middle part, the center of mass. Now, the parabola, of course, is the central center of mass, which behaves just like it's being acted upon by gravity, which makes sense because that's where it's experiencing the gravity force the most. The top is linear. Now, that's kind of interesting if you think about it, because why would the top be linear the whole time? Well, in my opinion, I feel like, I don't really know this for sure, but I feel like the top is experiencing this force of gravity, but it's also pushing, as I guess you could say, pushing the rest of the slinky out of the way. So the force it experiences is actually constant because it's experiencing a force down, but it's using that force to then push the rest of the slinky down. So that's my thoughts on it, and I just thought this is really interesting, showing how the center of mass behaves, looking at a graphical representation. So that pretty much wraps up my video about the physics behind a falling slinky. So just to recap real quick what actually happens. The top of it starts falling and the bottom stays still. Now this happens because it takes time for the information that the top has started moving to reach the other parts of the slinky, the middle, the bottom. You can explain this using the information as a wave, and it takes time for the wave to travel and for the bottom of the slinky to know that the top has started falling. And once it knows that, that piece that received that information then starts falling. And so we say this using waves, and that wave is described by the center of mass moving. It's a wave of center of mass motion. And so I thought I'd end the video showing something really cool, which is, you know, how does this change if maybe we attach something to the bottom of a slinky? So as you'll see here in this short clip, we're going to attach a tennis ball to the bottom of the slinky and then see what happens. You may be surprised with the results. So after this clip, it's going to be over, so thanks for watching the video, and I hope you learned something.
So hard, motherfuckers wanna find me.